So hi everyone. So we are from group number 2. So our group gonna present about design of a pump as turbine for small scale power. So this is our group members. So first is Megason Anak Pira, and number 2 is Amirul Rashid bin Najmuddin, and number 3 is me, Muhammad Nazmi bin Muhammad Sabri, and number 4 is Muhammad Amar bin Shamsul Bahrain. So we're gonna present to you about design of a pump as turbine for small scale power. So firstly, for the introduction, so what is pump as turbine or PAT? So PAT refer to the practice of using centrifugal pumps in reverse as hydraulic turbines. So normally pumps are designed to add energy to the fluid, but when we change it to the reverse, so they can also extract energy from a flowing fluid and convert it into mechanical power. So basically, we change the function of centrifugal pump to be a turbine. For the literature review, so literature review number 1 is pump use as turbine in real world. So in real world, small-scale hydropower systems are often found in locations where water flow at relatively low head and moderate flow rates. So this paper offers a novel concept for developing Pakistan's energy by producing small hydropower using pump as turbine, which is form of renewable energy with lower environmental impact and has not been used in Pakistan previously. So as we know, pump as turbine is environmentally friendly, so it is very suitable for the rural area like Pakistan. So literature review number 2 is pump as turbine in micro hydro system. So micro hydro system typically designed for small-scale application in remote off-grid areas, traditionally utilize turbines purpose built on electricity generation. So for the versatility, PATs allow for their integration into various micro hydro configurations. So it is offering a flexible solution that can harness energy from natural water flow like river, stream, or irrigation channels. So the pump as turbine concept in micro hydro system hold the potential to play a pivotal role in expanding access to clean and affordable energy in decentralized manner. So for the literature review number 3 is pump performance curve in actual. So the performance curve is a relationship between the pump's head and the flow rate. So as you can see in the diagram, when the flow rate increase, the head delivery head decrease. So the maximum efficiency varies according to the type and size of the pump. So as you can see in the diagram, the intersection point is actually where is the actual operating flow rate and actual operating head and efficiency. So the maximum efficiency varies according to the type and the size of the pump. So but it is typically between 40% and 80%. So as you can see the diagram, for the reference we get from Vogue M. So literature review number 4 is pump as turbine curve in actual. So it is primarily necessary to select the correct category of pump for the actual PAT setup. So and it is also necessary to determine whether the pump operates in turbine mode before installing it. So many scientists investigated this issue and proposed various relationship for pump selection. And suitable pump are determined by discharge capacity in meter cube per second and head location in millimeter and initial investment cost, and initial setup cost. So as you can see in the diagram is the pump as turbine curve in actual. So we get it from Vasquez DP Uri. So next is theory. So there are two theory in our presentation. So firstly, pump as turbine is a system of renewable energy idea based on the clever reverses using the standard pump function in order to capture the kinetic energy of flowing fluid for power production. So basically, we are using the typical pump and change it to the turbine to produce a power. So second theory is the pump is changed into a turbine in this novel way, with its impeller arranged to take energy from the fluid in the opposite direction of its typical pumping action. So uh, basically for the pump is actually uh, a fluid is actually receive the energy from the pump. So for theory number 2, actually we change the pump into a turbine. So the fluid is actually give a power to the turbine and change it into the mechanical power and then change it into the electrical power. So next is conversion of kinetic energy. So the impeller converts the kinetic energy of the moving fluids into mechanical energy. So this mechanical energy may then be utilized to operate a generator and then generate electricity or do other form of mechanical activity. So number 2 is flow reversal and hydraulic efficiency. So pump as turbine, as we know, operate by reversing the flow through a pump, so causing it to function as a turbine. So design consideration is focused on achieving optimal hydraulic efficiency during this reverse operation. And next is energy recovery in water distribution system. So the theoretical framework expands to applications in water distribution system where PATs can be employed for energy recovery. So the design theory involves integrating PAT system into water supply networks to capture excess uh, pressure and convert it into electricity.
Hello and a very good day. My name is Mama Amma Bishamsul Maharin. My metric ID number is MA22007. So for this slide, I will talk about why PAT system is more effective than commercial available turbine. So basically PAT, which means pump as turbine, it is expected for a PAT to work less efficiently than a regular turbine. This loss is an advantage of using a pump for micro generation. So with a proper research, this type of steam may be improved in order to provide an excellent alternative to traditional hydropower and electricity. This is why understanding the operation of pumps as turbines, which is PET, may prove beneficial. So can you see this table? So why is PET is very effective than turbine because the investment cost for PET is very low, while the turbine is high. PET is easy to install and monitor, while turbine it is complex installation and the maintenance cost is very high. For PET, there are many spare parts are readily available and easy replacement. For turbine, there are very few local supply, and a pump is much cheaper than a turbine because of widespread use in many hydraulic installation, while turbine is much more limited use. For this slide, I will talk about the most common pump used in PET system. So the first one is centrifugal pump. Centrifugal pump are frequently employed in PET systems due to their simplicity and efficiency. It is also the popular choice among other pumps because their straightforward design and ability to handle various flow conditions make them a popular choice. So centrifugal pumps excel in application where a constant, reliable power output is essential. Next one is axial pump. On the other hand, are known for their capability to handle high flow, low head conditions. Uh, why axial pump is a valuable choice? Because their axial flow design allows for efficient energy conversion in scenarios where a steady and substantial flow of water is available. So the next one is mixed pumps, which is the combined element between centrifugal and axial pumps, offering a versatility across a range of flow conditions. Their hybrid design allows them to strike a balance between efficiency and adaptability, making a mixed pump a suitable option for various pet installation. So the last one is radial pumps, also known as franchise turbines. It is recognized for their effectiveness in medium to high head conditions. So their radial flow design enables optimal energy extraction from water at elevated pressures, making them an excellent choice for pet systems. So for this slide, I will talk about the application. The first one is micro hydro, which is the primary application of pet systems. These systems harness the power of flowing water in small-scale hydroelectric setups, providing a reliable and renewable energy source for remote or off-grid communities. The next one is picohydro. These systems are designed to generate power in low flow, low head conditions, making them suitable for decentralized energy solutions in rural areas. The next one is irrigation system. So for application irrigation system, as water flows through a turbine, it is not only generates electricity but also aids in pressurizing water for irrigation purposes. So the last one is water supply network. So PET systems are increasingly being integrated into water supply networks. The application is by harnessing excess pressure in pipelines. These systems generate electricity while maintaining a reliable water supply. For this slide, I will talk about the main components of pump as turbine, which is PET. So the first one is impeller. So the primary function is to convert the kinetic energy of the fluid into mechanical energy. The mechanical shaft connects the runner or rotor to the generator or any other mechanical system that will convert the rotational energy into electricity or perform useful work. For the casing, surrounds the impeller and other components, providing structural support and also helping to guide the flow of the working fluid through the system. For the component generator, it converts the mechanical energy from the rotating shaft into electrical energy. For the rotor components, it is to rotating the rotating component that captures the energy from the fluid flow and transfer it to the mechanical shaft. For the working principle of PET, the working principle of using PET for small-scale micro hydropower involves repurposing a centrifugal pump to act as a turbine. In a PET system, the direction of fluid flow is reversed, as you can see in the graph in the figure on the right side. For the pump mode, is reversed to the turbine mode, which is the inlet is from there and the outlet is different from the turbine mode. So the system utilizes the kinetic energy of flowing water to rotate the impeller. Water from a source flows into the discharge port and the impeller, now acting as a turbine, extracts energy from the flowing water. For conservation of energy in PET, as water passes through the impeller, the kinetic energy of the flowing water is converted into mechanical energy, causing the impeller to rotate. So the rotation of the impeller is transferred to a shaft connected to a generator, which I said before, converts the mechanical energy into electrical energy. So the impeller interaction. It is a critical component of the pump, is in charge of receiving kinetic energy from the moving fluid. The impeller's blades contact with the water as it enters the pad system, causing the impeller to revolve. So next one is mechanical energy conversion. The rotation of the impeller converts the kinetic energy of the flowing fluid into mechanical energy. And then the mechanical energy generated by the impeller is then transferred to the shaft connected to a generator or other mechanical components. So the last one is electricity generation. The mechanical energy transferred to the shaft is used to drive a generator, converting the rotational motion into electricity. Alternatively, the mechanical energy can be employed to perform various types of mechanical work depending on the specific applications.
My name is Madison. For the project detail, in this project, we designed a pump as turbine using a centrifugal pump. As we can see in the picture, this one is the generator and fit to the feed pump into the inlet and the outlet. And the pump is the main component that is used in this project. The use of centrifugal pump as turbine may minimize the installation cost. Also, this project we analyze the piping system and selection of feed pump that I mentioned before is to convert the hydraulic energy within the feed pack into the mechanical or electrical energy. We go through to the performance equation. So this is our design pipeline system in pump as turbine in small scala that we apply in our project. First, we calculate the major losses that occur in our pipeline system. For this pipeline system, we use the PVC pipe as our experimental setup that we get from the case study. First, we calculate the hash of the pipe with using the formula P equal to rho GH, and after that, we calculate all the total major losses in the PVC pipe is with that we get 0.1482 meter. Still in the minor losses in the pipe, the pump piping system has two 90-degree bend, so it occur loss at fitting, which is expansion occur in the pipe. The head loss at expansion fitting that we calculate is 0.152 meter using the head loss equation, and to determine the velocity is equal to flow rate divided by area. Next is we calculate the loss from fitting and contraction in the pipe. Same formula that we apply to calculate the expansion in the pipe. The head loss at contraction fitting that we calculate and we determine is 0.112 meter. Next is another minor losses in pipe, which is losses at bend and losses at valve. So the total head loss is determined by adding all the majors and minor losses that along the pipe, and we get is 0.4345 meter in our pipeline system. Next is the selection of centrifugal pump for pump as turbine. The model of centrifugal pump that we use is Petrolo CP130 water pump. The flow rate at best efficiency point that we get is 0.009975 meter per second, and head at best efficiency point that we calculate is 16.5. So the pump efficiency that we obtain from above is we using the motor efficiency of 75 and rate power in kilowatt at 1.1. After we substitute all the value and we get the efficiency of our pump efficiency is 68.36 efficiency. Next is the initial selection of pump as turbine head and flow rate. The power is proportional to n power 3. So the speed of motor that we obtain is 2910 rpm, and when it's running as generator, the speed of generator that we get and calculate is 3090 rpm. Next is the relationship of affinity law that we use to determine the best efficiency point of the pump when it running as turbine, and we get the head of turbine is 29.37 meter. So the available hydropower that we calculate is 412.01 watts. Next is the selection of feed pump. On this project, the feed pump that we use is the Precision GAT355A. This primary function of the feed pump in PAT mode is to convert the hydraulic energy within the fluid pack into mechanical or electrical energy. As the fluid flow through the pump is reversed, the impeller acts as the turbine, extracting energy from the fluid and converting it into the rotational motion. This rotational motion energy can be used to drive a generator and producing the electricity. Next is the pump and turbine expected result. So, from the test result, it's proven that centrifugal pump can be used as a turbine to generate the electricity. From the graph, it is shown the value of head hydraulic power are increasing when the flow rate is increased. It also shown that the value of hydraulic power is depending on the value of the head and the flow rate of the water.
So we continue to economic parts. This is important to enhance the economic feasibility and sustainability of this project. So the first point is the long-term cost consideration. It can be achieved by develop a long-term financial plan that includes budgeting for maintenance, repairs, and potential system upgrades. This helps ensure the economic sustainability of the pump as the turbine project over its life cycle. The second one is electricity tariff and revenue generation. We must explore available government incentives, subsidies, or grants for renewable energy projects. Many governments offer financial support to promote the adoption of the sustainable technologies. Next is the community local economic concept. It involves local communities in the planning, implementation, and management of the PAT project. Community engagement fosters a sense of ownership and ensures the project aligns with the community's needs and priorities. The next one is minimization of in maintenance costs. We can achieve that by implementing remote monitoring of and control system to facilitate the real-time performance tracking. This allows for early detection of issues, proactive maintenance, and optimization of the PAT system efficiency. Lastly is the minimization of investment costs. We can get it by explore the innovative financing models such as public-private partnerships, community-based funding, or crowdfunding to secure the necessary capital for the project. Okay, we continue to pros of the pump as turbine. First one is energy recovery, where can this the water can be used in application where fluid is being pumped to capture energy, otherwise be waste during the breaking process. The next one is environmental impact, is making them more energy efficient. And also the pump as turbine did not release any waste to the environment. Third one is cost effective, because pump as turbine is more affordable and less expensive than all traditional turbines. Lastly, the design is simple. The pump as turbine design is simpler than the traditional turbine design, so it leads to easier maintenance and lower manufacturing costs. So we move from the pros to the cons of the pump as turbine. Okay, the first one is lower efficiency. As we know, when combined the pump and turbine typically have lower efficiency. Second one is gravitational risk. It will result in cavitation, which may harm the pump's internal parts. Cavitation will occur when the liquid in a pump turns to a vapor at low pressure. It occurs because there is not enough power at the suction end of the pump or insufficient net positive suction head. When cavitation takes place, air bubbles are created at low pressure. So when combine the pumps and turbine together, it will occur the cavitations. Next is the limited performance analysis, because it is occurs because pump as turbine is not widely used in the industry, so it's challenging to predict their performance accurately. Lastly is the limited flow range. Limited it's because limited operating range compared to turbines or the old turbines. So we move to the conclusion of our project. Okay, the first one is the pumps as turbines. PAT is known concept of using excess flow and pressure to run a pump in reverse to generate electricity. And then we have analyzed the performance curve between pump and the pump as turbine. In summary, analyzing the performance curve between a pump and PAT involve understanding the characteristics of both devices, their individual performance curve, and identifying operating points for efficient energy conversion. This integration is valuable for energy recovery and also the optimization in various applications. Okay, the third one is we have learned the working principle of PAT and then runs the performance equation on case study of pump as turbine in small scale. And next is we analyze the economic analysis in pump as turbine industry. So a comprehensive economic analysis in the pump as turbine industry involve evaluating capital and operational costs, assessing energy savings, calculating the return of investment, considering life cycle costs, addressing risks, and ensuring compliance with regulations. Uh, the decision based on these factors is crucial for the successful deployment of an economic viability of pump as turbine system. Last but not least is we investigate the pros and cons of PAT in real world applications. Okay, for the last part is the question and answer. Here are some questions that you may ask for our project. The first one is what are the benefits of using a pump as a turbine for remote area hydro project? Okay, the benefits are reduce the installation cost, provide a reliable source of electricity in remote areas and green energy. So, while pump as turbine system offers several benefits, it's essential to conduct a true feasibility study to ensure that the specific condition of the remote area are suitable for this technology. Factors such as water availability, terrain, and community needs should be carefully considered in the planning and implementation of PAT projects in remote areas. Okay, for next is question 2. How does a pump as a turbine work? So as shown earlier in this presentation, the water flows through the pump in the opposite direction compared to its typical operation, which is reversible flow. And last question is where are pump as turbines commonly used? Okay, the pump as turbines are commonly used in a small scale hydropower application, such as micro hydroelectric system and water supply networks. Other examples of the use of TNT in the industry is for the irrigation system, industrial process, wastewater treatment plants, mining operations, aquaculture and fish farms, micro and pico hydropower projects, community-based renewable energy projects, water pipelines and networks, and lastly, at the decentralized energy generation. But it is important to note that the sustainability of PATs depend on the specific condition of the site, including water flow rates, heat, and the overall hydraulic profile. Careful consideration of these factors is essential for the successful of implementation of pump as turbines in various applications. Okay, I think that's all from me. I'm Rashid bin Najmuddin, my metric number MA21011, and thank you very much. We hope that the pump as turbine will be widely used in the industrial in future. Thank you.